Okay, so we continue review/preview of linear algebra. Okay, so what we were looking at last time was how to use coordinates to calculate distances, to calculate rather than measure. Okay, so as you can see, we end up with dimension 1, simply the absolute value of the difference on left, right, over here. Then in dimension 2 is this, the familiar distance formula, and then the familiar distance formula is expanded to, and we'll talk more about that, to square root with 3 terms. Similar, once again, distance formula. When it is 4-dimensional space, it will be 4, and so on. Okay, so it is entirely about the Pythagorean theorem. So because if we are now at dimension 2 and we understand the distances within a plane, then what happens is we add a third dimension like this, the z-axis, and look at it. We're going to talk about that too. Every line within our plane will be perpendicular to the z-axis. And once again, we have a bunch of right triangles, and we have the Pythagorean theorem to use again. Okay, so that's where that formula comes from. But there is a second question here about the geometry. So geometry is what we're talking about. There are 2 issues of geometry, and the second one is, so this is number 1, and the number 2 is how to use coordinates, once again. How to use coordinates to calculate what? We can calculate distances. What else we do and want to calculate in geometry? Angles. We can calculate angles. Okay, so there are 2. So the distances are pretty much solved. The angles is more complicated, but at least we know a little bit how to deal with it. And we'll just look at the picture in the middle, a little bit small, but we could ask ourselves, for example, what is, how about this angle? So we have 2 points. At the 2 ends here and there. Okay, and then there's a straight line between them. And then what we are asking ourselves, what angle this straight line forms with the x-axis. So what is the line? What is the angle formed by the line from P to Q with the x-axis? Something happened to the.
Yeah, I don't know.
Something happened to that thing, not to the. Something happened to the projector. I do.
Fix the arrows. There should be arrows in there. Maybe not.
There is maybe let's see. Yeah. Let me see there. Yeah, so it doesn't cut too much, but I don't think you see here any arrows over there.
I can't really see what those are. It looks like there could be arrows, but it also looks like they're just like buttons.
Yeah, it could be. Okay, so we'll just, it's not too much. I mean, we're not just telling you where I'm going to roll, and I'll just stick to it. Just scroll it up. Okay, so once again, the angle formed by the line from P to Q, the picture is right there. We know about P and Q only 2 things, and that is their coordinates, A, B, C, D, and how do we find the angle? So I'm only bringing up this question because, as a part of review, because you know the answer. What? Well, use the. I mean, think about it. Think about it. It is nothing but a triangle, a right triangle, and we just established. We just found the distance, the sides. So what is it? How do I find the angle from the triangle with known sides? Trigonometry, right? Specifically, what's the function?
It's like inverse tangent.
Tangent. Right. So this is c minus a, right? And this is b minus d. Okay. And then if this is the angle we're talking about, it will be the tangent. So if this is say theta, so tangent theta is equal to the opposite over the adjacent, so b minus d over c minus a. Okay, so as you can see, it can be done, even though it is a bit awkward, and we'll certainly see better ways to do it. But this idea comes from this is what is the tangent in a more elementary context. If we have our function y equal mx, okay, and suppose this is my theta, the tangent theta is what? I'm sorry. Y equal mx is our line, and the angle is once again between the line and the x-axis. What's tangent theta? No, this is tangent. Tangent express tangent theta in terms of m. Do I need to draw a triangle here? Maybe I also need to mention, yes?
It equals, it's y over x.
Right. Okay. Can you, so this is the run, this is the rise. Okay, so tangent theta is equal to?
Rise over.
What?
Rise over run.
Right. Which is equal to?
This one.
Which is? M. Okay. Okay. Okay, so that's we're gonna do more and more of that, and you realize that once you go to high dimensions, the just one dimension up, and the complexity increases because we are not going to be talking about. We'll be looking at picture more of what's on the right. We'll still be interested in angle between lines. Okay, so that will be just one angle. But if you're talking about a similar situation to what we have on the right in high dimension, it will be a plane. It will be a plane, and plane will have two slopes. So this one and that one. Okay, so that the complexity we're gonna face eventually. Okay, so once again, we're just connecting to something that we've seen before. Okay, so a couple more words about relations. In fact, a good way to remember what they are is implicit. Implicit relations versus explicit relations. The letter is simply functions. So y equal x squared, that's our function. Well, suppose nonlinear for the time being. X squared plus y squared is equal to 1 is an implicit relation. So there's a relation between x and y, but there is no. It is not as explicit as a function. So at best we know that's a circle, but it is. We do know that it is circle. The question becomes, what is that we do in order to find? So what is it? it is very easy to answer the question for that the function explicit function, because how do I do it? I can simply plot it. How do I plot it? How do I plot the function y equals x squared? Suppose that you don't know any calculus. What do I do?
0, 1.
How do I plot a function y equals x squared?
You evaluate it from points.
They're different points. Yeah, so point by point, as many points as you like, as you need, you plot them in the, so say 0, 1, 2, 3. You can have 100,000, and you have 0, 1, 4, 9, and then you plot these. These are points. Each of them is a point, and you can have as many as you like, and if you have enough of them, they form a curve. Whether these functions are linear or not, it's the same story. Similarly similar situation on left when the relation is implicit, and suppose we have that equation over here, x squared plus y squared is equal to 1. How do we plot it? How do we plot it?
Solve for one of the variables.
Right. Well, suppose we don't know any algebra, because this is a simple equation. You can imagine an equation that is way more complicated, and algebra may fail every time. You don't know whether your algebra skills are good enough, or maybe it simply doesn't matter how good you are at algebra. It might simply be impossible. Okay. So some equations have no solutions, or no explicit solutions. Okay, so imagine that you have some complicated implicit relation. How do you plot it? How do you plot that relation? Well, first of all, what is the plot? A plot, or the graph. The graph for a function is the graph. So is the set of all points x, y on the plane that satisfy the relation or equation. The relation. So it was very easy to, on the right, you plug in x and you'll find y, and you immediately form a pair, which form a point. You plug that point, you have your curve. What do we do on the left?
Now use math, you just gotta guess to find two numbers that add up to 1 squared.
That's right. So in other words, trial and error. The answer is trial and error. It is not as straightforward. So every computation on the right will give you a point, right? As long as it's still within the domain. On left, you might fail. So for example, I will just try, and I have say 0, 1. 0 squared plus 1 squared is equal to 1. Yes. And then 1, 1. 1 squared plus 1 squared is not equal to 1 squared. So no. And then you keep going until you have enough points. And the trouble with this is a very theoretical point of view. So since we have a few or several computer science majors here, let me show you what I did, some unrelated subject. What would one do to plot a graph of this of our implicit relation? Where is implicit? Here it is. Oh, here it is. Okay, so the trouble is that if you carry out actual computations, it's never equal exactly to that number. Okay, so as you can see, I had to go. You have this field. This is large enough. So this is Excel. Okay, what I do here is I have a table of x and y values which run through the whole screen. So all of these values that you see that on the plot. All x's and all y's are being run through, and these are this is how they are happening. These are x and y's. As you can see, as I'm starting to run through the values, y's are all equal to -1. So I set y equal to 1 and then running through these. Then I move on a little bit up, run through all of these, and go up, run through all of these. Have to test them all. How? Now, how do I test them? I compute x squared plus y squared minus 1, and this in the next row, next column. And then, well, these are give a bunch of numbers. None of them is exactly equal to 0. Look at it. Okay? So, by the way, how many points do I have here? Well, you can imagine that, where's that thing? On and on, it's 1,000 points or so. Okay, testing. Instead of with the function, all you need is maybe 10, 20, 100 points at most. Here I have to test 1,000 points, and still it's not very works out easily because the number is never exactly equal to 0 because this is computer. Okay, so what do I do? Or you tell me what I do. Which point to plot? Or what did I do? You can actually see here that I establish error threshold for the error. And if the error is less than a certain number, I plot it. If it is larger, I do not plot it. Okay, so for example, over here, where's that? See over here, I plot a few points. Why? Because the values of my function are fairly small, and the rest are not being plotted because they're fairly large. Okay, so this is my error that I want to. Unfortunately, it is a variable. So if I put, for example, if it is too large, what's going to happen? If my threshold is too large, what's going to happen? Too many points. For example, if I put here, say, 0.3. Oops, whatever the hell happened. Enable editing. Okay, so if I put the error 0.3, what is your problem? Whatever happened? Okay, so that's no. 0.3. Enter. Okay, too many points. It is not a curve. We know it's supposed to be a circle. Does it look like a circle? And if I pick the error too small, threshold is too small, 0.2, what do I get? Maybe not enough or maybe nothing. So this is actually, 0.02. Too thin, and if I make it even smaller, then there will be nothing left. So anyway, so just a little demonstration, but you can see how that's why we care about functions so much, and we are not satisfied with the relations, even though they're similarly algebraically seem very pleasing, but only the case when we actually know what's behind it. So we know that what's on the left is a circle, and say 3x plus 2y is equal to 1. That is a straight line. But if I did not know that it's a straight line, I would have exactly the same problem plotting point by point, and once again not knowing which point to plot, which one I don't plot. Okay, so the bigger idea here is the idea of the graph. Unfortunately, here's my pen is malfunctioning a little bit, but so as you can see, my letters are being connected to. See, I'm just putting points, point after point, and they're being connected by. Okay, well, there's something wrong with the pen. Yeah, no, it's some setting. There is some setting that it has happened before. I have to, after class, I'll look into it, how to fix it. So it tries to connect everything as if I am drawing some board. Yeah, it looks pretty awful. Anyway, so the graph, that is the idea, which is right here, is written pretty much almost the definition of the graph. So, but this time we usually speak of the graph as the graph of a function. So y equal f of x. The graph is all pairs x and y such that they satisfy this equation, this relation. Okay. So we don't care as much anymore about functions that are not linear, and which means that the graphs are very simple in case of linear functions. These are the only linear function. This is the only linear function in dimension 1 that we know there is. So the only variable part is m, and so all graphs are straight lines. All graphs of linear functions are lines, straight lines. Okay, but you can imagine what happens when we go into high dimensions and we have more and more variables to deal with. So, for example, a function of 2 variables, its graph will be a plane. But the idea of the graph is still the same. It is you take the domain, you take the range or the codomain together like this, and then you have a pairs of points or in the domain and the codomain, and they together form points in this bigger space. So that's why, even though the situation is one-dimensional, as I said, the input is one-dimensional, output is one-dimensional, but the graph lies in the two-dimensional space. We have to add the dimension. So if you have 2 variables, then you already have your graph will be 3-dimensional. So just very simple situation. You have the input, 2 numbers. Okay, output still 1 number. And you will immediately have a 3-dimensional graph. You go 1 more dimension, it becomes 4-dimensional, and we cannot plot it anymore, unfortunately. So, but the idea of the graph remains, so we'll have to deal with the graph, understand it, and use it without actually seeing it, unfortunately. Okay, so functions are, so we even though this is the example of a linear function, there is nothing else in dimension 1, we have to take a broader view and look at functions as correspondences. So, once again, this is what the function is, x, y, f, and as you can see, it is some kind of rule or a program, if you like, that converts x into y. Okay, the converts x into y with the domain supplied. The domain will always be assumed to be supplied with the function itself. No trouble when the function is linear. There is no division. There are no square root. Nothing like that. So the domains will be everything available. So no trouble. But it is important to always to know that if we say that the function is defined, f is defined on, say, R, the reals, it means that every single x is available. Every single x will plug in, it works. If we say that it is R squared, the plane, that every pair of points is then available. If we want to restrict the domain, then we do so. Then the function then it will be different. So the function defined on the real line and the same exact function defined on interval, say 0, 1, these are 2 different functions. So once again, f of x equal to, say, 3x on negative infinity to infinity, or f of x equal to 3x on 0, 1, these are different. Okay? So, now, once again, we are not going to be living in one-dimensional space for long. And so already this thinking about functions as this kind of a black box machine converting input into output, you realize that x could be anything and y could be anything. In the context of linear algebra, these will be points or vectors, depending on your point of view. More likely vectors. So vectors, and these are also vectors. Okay, so once again, we convert one into the other, and the vectors could live in different dimensional spaces. Like I said, if we're talking about a function of 2 variables, you can say that these are 2-dimensional vectors, but the output still could be 1-dimensional. So that creates a new type of function. But still, that's just a preview part. The review part is about the why this kind of diagram is so helpful is because the most important operation of functions, as we will see, is a composition. And so when you have a diagram like that, it is very easy to visualize compositions as simply 2 diagrams like that wired together consecutively. Okay, so x is input and y is the output. What if we have another function? Maybe it has nothing to do with it, but the outputs are y's, and inputs are y's, outputs are z. So this is G. So we can form a composition how we wire these two together. So we're making sure that whatever comes out of F will be plugged into G. Okay, which creates a new function. Okay, that's a big deal. How we create new functions from old. You probably saw a lot of that in Calculus 1, but the composition is usually not overemphasized because there are other operations just as important. But really compositions are the most important. Here's let me form the new function. This is the new function. Okay, so once again we create a bigger black box with one still input is visible, X. And the output is still visible, that is Z. What's happening inside, we may or may not know. Once again, the point is to form a new function, and whatever the notation we use for it is nothing but a name of a new function. So what's the name of this new function? If one function is f and the other one is g, what's the name of the new function?
F of G.
What?
F of G.
Almost.
F of G of X.
Be careful again. Take a careful look.
Z.
No, it's not f of g of x, it's g of f of x. Look at the order operations. We always read from inside out. So first x, and then f of x. And then that is y, right? And then we have z equals g of y. So what do we do with these? We substitute. So this y goes in here. So we have then z is equal to g of f of x, right? The unfortunate thing that we have to read this algebra from right to left, as you can see once again. So if you want to, from what I have over there at the end, if I try to recover the original, then as you can see x, then I apply f, then I apply g in that order, in the opposite, so right to left, unfortunately. But actually, this is not the name of the function. This is how you compute it. So this is the algebra. The algebra that corresponds to this diagram. So if you're writing a program, this is how you would create that program. This is how you would outline the program on a whiteboard to plan your work roughly. But what's on the right is a more mathematical way of doing it, but it's exactly the same thing. So for f, x to y, and from y to z, and then the functions are called f and g, and this is how we denote it. But there is a special notation for compositions. F and g, how? Remember the name with the little circle? I mean, there is no name. The name is composition, but the notation is once again in the wrong order. G circle f. That's the new function. Okay. So once again, if you look carefully at it, at what I just wrote up to this point, below this line, even though initially we probably were thinking about numbers, but really, and that's what Calculus 1 is, but at this point you have to start learning that it doesn't have to be. X could be anything, Y could be anything, Z could be anything. Okay, so functions are understood in a very abstract way. So is there a formula? Maybe there is no formula. We just want to, we know what the composition is, no matter what those two functions are. We just wire them together consecutively, and the operation is one of several operations on functions, but I do think it is the most important. Okay, so some kind of program or rule or formula certainly is a possibility. All good descriptions of a function. Okay. Another one is less formal. Is the graph itself. The graph itself might also serve as that rule. So if we have the graph, we know how to plot the graph. We just talked about it. How do we use the graph to evaluate a function? So evaluate y equal f of x from its graph. Remember this one? How do we evaluate it?
You know, if you're given one,
Yeah, x, right, x.
you just kind of vertical line,
Reverse the line.
divide that over the y-axis.
Yeah, find the intersection of the vertical line with the graph, and then what? And then do a horizontal line, right? So do a horizontal line and find the intersection with the y-axis, and then that will be the output. So once again, input over here on the x-axis, the axis of inputs, and the output is on the y-axis. Okay, so in that way, it is a kind of a rule what you just described. Those two steps could be thought of a description of a function. So there is a graph is given, and then using this algorithm of drawing a line, intersecting, drawing the other line is that rule or program of how to find that number. It will be approximate, but it is okay as an idea. Okay. Going to test the graph point by point. Okay. Good. So once again, back to linear functions. Y equal mx. Very simple class of functions. We can also say something from calculus about functions. What did we learn in calculus 1 about functions? What is one of the most important characteristics of a function? So y equal f of x equal to 3 of x. What's so special about it? It is increasing. Okay, so then there is a very simple classification of linear functions in terms of their monotonicity. So in terms of f, in terms of m. So remember, y equal m of x is increasing if what is the derivative? The derivative of mx? No. What? Y equal mx, the derivative is m. The derivative is m. So whenever the derivative m, also known as the slope because it's a straight line, whenever it is positive, we have an increasing function, and it is decreasing when it is negative. And then there is also constant if m is equal to 0. It also nicely matches that idea that we discussed last time. It is the functions being one-to-one onto.
Can you scroll up a little bit?
So these two are one-to-one onto, and this one is not. There's only one boundary. However, then once we go into high dimensions, that nice classification will have to be amended because things are more complicated. You think about the plane. Depending on which direction you go, you might be going up or you might be going down. So that is we'll have to worry about that. Similarly, there might be the one-to-one onto idea might be also not as easy to establish as simply looking at one single number. So we'll see that later. Okay, what else? Okay, so we'll encounter polynomials later on, so I don't want to review polynomials that much. So we're not studying polynomials, but we will be using them. So polynomials, so starting with the quadratic formula, but when we get there, we'll review it one more time. Okay, polynomials will be, but not much else. Okay. Just a minute. Okay, so more operations on functions. So operations on functions. Number one, always. Usually it's number 5, but always is the composition. Number one, composition. Composition. Okay, but there are others. So remember operations on functions. From calculus or pre-calculus. Yeah.
Exponents.
No, operations on functions, which means that it is an analog, pretty much, of operations on numbers. There is no composition of numbers, but there are 4 operations on numbers, and we can have 4 operations on functions. So addition, subtraction, multiplication, and division. Okay, so like I said, we're not going to be doing this. No, at least not entirely, and because the division will take us, and multiplication too, if we're not careful, will take us away from linear functions. So, for example, y equal 3x and y equal 4x. It is okay to add them together. It will be 7x, y equals 7x, the sum, right? But it also is okay to subtract naturally. But if you try to divide, y equal to 3x over 4x will equal to 3/4. What's the problem? What? It is constant. Constant which is not 0, which makes it what? Nonlinear. It is a nonlinear function. Remember that we talked about that in the beginning, that the linear functions are the ones that have 0. Not only they have y equal mx, pretty much all there is. These are the linear functions. So if there is a y-intercept which is not equal to 0, such as a constant in particular, then the function is not linear anymore. Multiplication 2, I skipped over multiplication, but 3x times 4x, it gives me 12x squared. Okay, so it's quadratic, once again nonlinear. So there is, however, an XOR operation that is allowed, and that multiplication is allowed. We are allowed to multiply a linear function by constant. Okay, so that makes pretty much 2 operations still available. So addition. I don't want to include subtraction. Addition. So let's say number 2, and number 3, scalar multiplication. Or another one, maybe a better way to put it, familiar term is constant multiple. Remember that, right, from calculus. So if I have 3x, I could multiply the whole thing by 5. And that will be still 15x, and it is still a linear function. Okay, so actually so once again, we're trying to have operations on functions. We ahead of time, studying linear algebra, we limit ourselves to linear functions only. So we want to make sure that when we carry out these operations, we will not suddenly leave that domain of linear functions. So as we have noticed that, it's probably very easy to demonstrate mx plus nx is equal to m plus nx. So here I took 2 linear functions, absolutely arbitrary, mx and nx, added them together. What's the end? The result is, once again, a linear function. So this is okay. Constant multiple, the same thing. So if I have a linear function, y equal mx, and multiplied by any number, so mx, and then multiplied by k, what do I have? kmx. And it's, once again, it's okay, a linear function. Okay? That brings me back to the number 1 operation, that's a composition. So the question becomes, let me first scroll. Okay, so let me state this. Let me state it. The sum of 2 linear functions is a linear function. A constant multiple of a linear function is a linear function. So it's there's 2 and 3, and then number 1 is the composition. So the composition of two linear functions, once again, okay. So let's analyze the last statement a little bit. The composition of two linear functions is a linear function. Can you argue that this is the case? So how can you explain it?
I mean, just feel like it showed numeric linear functions and add them.
No, you don't add it. This is composition.
Oh, composition.
Composition.
The second function is linear,
Yeah.
and the first one's just going to give you a number output,
Yeah.
which as the input to a linear function keeps linear.
Right. Can you be more either you can either algebraically demonstrate this is the case just in the same manner as I did over here with okay and okay. So can you demonstrate it in a similar fashion to what I have over there? Well, so let me get started. The first one is y equal mx. What's the second one? Be careful. The first function is y equal mx. What's the second one? That's right. Is equal. Thank you. And y. That's right. So as you can see, the variable is the output of the first is the input of the second. So these are the two functions that we can now compose, and the composition is just another word for substitution. Okay, so I substitute the first into the second, and I have z equal and y and mx, which is equal to, once again, n mx. Okay, so all of these computations that we have seen will appear later in a high dimension. It will be amazing to see how many things work out in high dimensions just as well as in lower dimensions. So, another way to see it, if you think about linear functions as multiplications. So, what is a linear function in dimension 1? Simply we're multiplying the input by a fixed number every time. Okay, so then two consecutive linear functions you multiply by one number and then by another number. So the result is once again just multiplication by a number. Okay, so that's these are the three main operations. We'll just see them in a different context very soon. Okay, addition, subtraction. So subtraction, once again, I dropped the subtraction. Why? Because, why did I drop the subtraction?
Adding a negative.
Adding the negative. So you take the second function, multiply by -1 using the constant multiple, and then subtract from the original. So we don't really want it. But now 2 and 3 can actually be combined together, and it is called a linear combination. It's like mx plus n1, mx plus nx. Okay, so simultaneously multiply by the two functions that you. Well, that's not what I meant. What I meant is if I have one function nx and the other one is mx, I can form a linear combination a nx plus b mx. Okay, so a linear combination has simultaneously constant multiplication and addition. So it's like two operations, two birds with one stone. Okay, another little topic is, but very important, is change of variables. We already talked about that a little, but let's do a little bit more of that. And that is change of variables. If you want to remember where it comes from, is a change of units. Okay, so you have a function, and then just it's maybe the input is x, maybe x is time. How about x is time? And it is measured in seconds. Okay, and then you have a new function, and then you decided for some reason then now still have time, but is measured in minutes. I think I'm mostly out of time, but you can see where we're driving at. We'll have to have a new function. And if you can tell me what operation I'm going to be using here. No, I mean it will be multiplication, but ultimately you change the variables, and then the change of variables will be a function composed with your function, with the original function. So this is about compositions. Okay, so I'll see you next week.